Okay, welcome back everyone. So this video is a little bit different. I kind of want to show you a trick for solving inelastic collisions, and this is something that I actually learned when I was a TA for an undergrad physics class at U of I. So this is some kind of advanced stuff. The math is pretty easy, but the reasoning behind it is kind of tough. Okay, so here goes. Let's go back to the Jack and Jill problem, and that was, again, I believe number 84 on page 212. And what we had was Jack was 290 kilograms going at 2 meters per second, and Jill was 325 kilograms going at 3.5 meters per second the other direction. So this is an elastic collision. We had just an absolute ton of algebra, and then we finally came up with our answer after, well, when I worked through it, it took me about 25 minutes. So this method that I'm going to show you will take you about 2 minutes. Now, there's 4 steps. So this is sometimes called the 4-step center of mass 4-step center of mass method. Sorry, for elastic collisions. Okay, so the first step is actually to calculate something weird, which we call the velocity of the center of mass. And this is really just a weighted average of all the different objects in the system. You take their masses, you multiply by the velocities, you divide by the total mass. So the definition of this is basically the sum of each of the masses times each of the velocities divided by the sum of the masses. And if that looks kind of weird to you, basically what it is on the top is the total momentum of the system, and on the bottom is the total mass. So you can think of it as kind of an average velocity of the system. So here's how it works. In this case, the velocity of the center of mass is going to be 290 times 2 plus 325 times negative 3.5. That should look familiar. That's what we had to do previously to calculate the initial momentum of the system, and now we divide by the total mass, which is 615. So this gives us negative 0.9065. And one way to think about this for the center of mass is that there's an imaginary floating object called the center of mass, which is moving in the negative direction at 0.9065. And it's important to draw that for the next step. And in the next step, what we do is we basically convert the initial velocities to the center of mass frame of reference. In other words, if we were moving with the center of mass, what would our velocities look like? Okay, and the actual equation looks like this. V1 initial center of mass is equal to V1 initial minus V center of mass. And so let's try this with Jack. Jack is moving to the right at 2 meters per second, and we're going to subtract off negative 0.9065. So compared to the center of mass, Jack looks like 2.9065. Okay, see if that makes sense. The center of mass and Jack are going in opposite directions. So yeah, it makes sense that you have to end up adding them. Now, what does the center of mass think for Jill? Well, Jill's going 3.5, so we're going to have to subtract. So V2 initial center of mass is V2 initial minus V center of mass. So it's negative 3.5 minus a negative 0.9065. And so as far as the center of mass is concerned, Jill is moving to the left, but not as much as we would think she's moving. In other words, since she's moving to the left and so is the center of mass, it thinks she's moving slower. Okay, now this is the step that you just have to trust me on. Now we're going to say that V1 final after the collision is the opposite of V1 initial. And I'm not claiming that this explanation is a proof. It is none such thing. Now the key is that this is an elastic collision, so that means that the kinetic energy before is equal to the kinetic energy after, and that's a hint. So if you want to try to prove this using kinetic energy, you might be able to get some extra credit on your homework assignment. So we just flip the signs, so this will be negative 2.9065 and this will be positive 2.5935. In other words, the two objects just bounce off each other, and from the center of mass point of view, they just rebound with opposite velocities. Now the fourth step is to convert back to the quote lab frame of reference. And in order to do that, we just take the equation from number 2 and we just solve it, but instead of i's we put in f's. So we have V1 final equals V1 final center of mass plus V center of mass, and V2 final is V2 final center of mass plus V center of mass. So that's going to be negative 2.9065 plus negative 0.9065, which equals, sorry I ran out of space, negative 3.81 meters per second. Then for Jill, that's going to be, let's see, plus 2.5935 plus negative 0.9065, and that's going to give us plus 1.68 meters per second. Okay, so I'm going to circle these guys. Okay, this is V1 final and this is V2 final. And let's see, conservation of momentum in one dimension elastic. Hey, remember this video? Magic algebra skills and all that? Okay, so we have 1.69, which is basically the same as 1.68, and then we have negative 3.81, negative 3.82, close enough, and there you have it. Now my explanation took about 6 minutes, but really you can distill this down to a very quick process. And so this is just a little extra added bonus for how to do center of mass, frame of reference, elastic collision problems.